Hey everyone, welcome to The Explainer. I am absolutely thrilled to take you through some genuinely fascinating new research today. We're going to be tackling one of the single biggest bottlenecks in modern artificial intelligence. We're exploring this brilliant architectural tweak that makes AI fundamentally faster by teaching it to do something surprisingly, well, human, to read smarter, not harder. The paper we are diving into is called Adaptive Computation Depth via Learned Token Routing in Transformers. All right, let's get right into it.
Now, to really wrap our heads around why this new research is such a big deal, I want you to think about something for a second. Do all words require the exact same amount of brain power? Seriously, think about how you naturally read a sentence. Your eyes effortlessly skim right over simple, predictable words, the, and, or just a basic comma. You don't even consciously analyze them, but your brain naturally hits the brakes and dedicates intense focus when you stumble across a complex scientific term or a totally brand new concept. Without even trying, you adapt your computational depth on the fly.
But here is where current state-of-the-art AI completely misses the mark compared to human reading. Standard transformer models, which is the architecture behind pretty much all of today's massive language models, they don't adapt at all. They process every single token through every single layer identically. They apply the exact same massive multi-layered computing power to a simple comma as they do to the absolute most complex rare word in the dictionary. It is, quite frankly, a massive waste of time and energy.
And that brings us perfectly into Section 1, the Transformer Compute Problem.
So for these large deployed AI models operating out in the wild, this incredibly rigid, fixed-depth processing creates a tremendous computational bottleneck in the inference stage. I mean, when you're serving millions of users, forcing a massive neural network to deeply analyze a predictable spacebar character is just ridiculously expensive. We really need a way to let the model exit early on the easy stuff. And that is exactly what this paper solves. They introduce a mechanism called token selective attention, or TSA for short. The core idea is that right after each transformer block, starting just after the initial stem block, they drop in this incredibly lightweight two-layer router. And this router basically acts like a traffic cop for every single token. It spits out a probability deciding whether that token actually needs more processing in the next feed-forward network, or if it can just bypass it entirely.
Now, the tricky part is how you actually make this function in practice without completely breaking the model's ability to learn. The researchers came up with this brilliant dual-mode mechanism. During the training phase, the router uses what they call soft gating. It scales the updates continuously, which is huge because it means the whole thing remains fully differentiable. The model can learn normally using standard gradient descent. No messy, complicated reinforcement learning required. But, and here's the magic, during real-world inference, it flips a switch to hard gating. If the router's probability hits a certain threshold, the token physically skips that heavy computation block. That translates to actual real-world flop savings. All right, let's unpack those mechanics a little more in Section 2, how TSA actually works.
You might be wondering, wait, doesn't adding a brand new router to every single layer just bloat the model? Surprisingly, no way. Because each router is just a tiny two-layer multi-layer perceptron, the total parameter overhead added to the base model is a mere 1.7%. It's an astoundingly lightweight addition for the kind of capability it unlocks. Now, before we look at the results, we need to make sure we're actually measuring success the right way. The core metric used throughout this research is TLOPS, which stands for Token Layer Operations. Very simply put, for each block in the network, TLOPS equals the number of tokens actually processed at that specific block. By tracking TLOPS, we get a super precise measurement of the compute being saved across all the different layers and tokens.
And this brings us to what is, in my opinion, the most mind-blowing finding in the entire paper. The researchers note that routing emerges from the task loss gradient alone, even at lambda equals 0. Okay, what does that mean in plain English? It means the router naturally learns to skip redundant compute entirely on its own. They didn't even have to explicitly force the model to save compute by using a depth regularizer. Just by trying to predict the next word as accurately as possible, the model realized on its own that processing certain simple tokens further was just adding useless noise. So it literally just learned to mute them.
Let's see this in action in Section 3, the Shakespeare experiment. To really kick the tires on this, the researchers decided to test this dynamic routing using the well-known Tiny Shakespeare dataset. They wanted to see if the model could genuinely learn which characters were essential and which were just filler. So I want you to picture this. What does it actually look like when an artificial intelligence learns to skim the works of William Shakespeare? If it's truly operating like a human reader, which specific characters or words would it confidently just gloss over, and which ones would demand its full, undivided computational attention? And the visual proof here is just awesome. In the mapped-out snippet of to be or not to be, the areas marked in green mean the token is fully active. The AI is firing on all cylinders, using all its processing power. But look at the bright red areas. That red indicates heavy halting. The model aggressively flashes red to skip computation on the spaces, the highly predictable punctuation, and those super common letters. Meanwhile, it stays dark green on the unpredictable, content-heavy characters. It is literally skimming the text based on how contextually difficult it is.
Now, the obvious fear with skipping all these layers is that you're going to ruin the model's ability to learn anything useful. But looking at the validation loss mapped against training steps, the TSA model perfectly matches the baseline model. It learns just as well, step for step. But then, when you map that exact same validation loss against cumulative T-flops, the TSA curve shifts vastly to the left. It's reaching the exact same level of deep understanding, but it's using drastically less computing power to get there.
So how much less compute are we talking about here? The hard data from the Shakespeare experiment reveals that the token selective attention model saved a massive 22.8% of token layer operations. Nearly a quarter of the entire computational workload was simply dynamically bypassed, all because the model knew it just didn't need it to understand the text. And what was the trade-off for saving nearly a quarter of the compute? This is the kicker. It came at the cost of less than 0.5% in quality loss. Literally less than 0.5%. It's a staggering efficiency gain with virtually zero penalty to the model's actual performance and accuracy.
Which leads us straight into our final section, efficiency meets real-world speed.
Because, theoretical math and token layer operations are great on paper, but the researchers needed to prove this worked outside of just Shakespeare. So they tested TSA against structurally diverse Wikipedia data, and they pitted it against a popular existing method known as early exit, and the results are clear. When matched at the exact same efficiency level, meaning both models were forced to skip the exact same amount of compute, the TSA model delivered a validation loss of 1.4482, which cleanly beats the early exit model's 1.4586. This proves that an end-to-end learned router, one that trains right alongside the model, makes fundamentally better decisions about what to skip than early exit, which just uses post-hoc thresholding after the model is already fully trained.
But let's be real, the ultimate test is always the clock. This completely grounds the theory in reality. Running inference on a standard off-the-shelf Apple M1 Pro chip, the baseline model speed sits at 1.0. But the sparse TSA model, running in its hard-gating inference mode, clocked in at a 1.023x speedup. The theoretical TL-top savings successfully translated into an actual measurable wall clock speedup on commodity hardware. The computer literally generated the text faster.
Now let's keep it real for a second. As with all cutting-edge research, we have to look objectively at the current limitations, and the researchers are totally transparent here. First up, this was tested at a relatively small scale of 5 to 6 million parameters. We still really need to see how this behaves on those 100 billion parameter behemoths. Second, that real-world speedup currently requires a batch size of 64 or higher just to overcome the CPU-GPU sync overhead. And third, right now they are only skipping the feed-forward networks, leaving the attention mechanisms entirely dense. Sparsifying attention is a much, much harder challenge for the future. But honestly, the foundation they've laid here is just incredibly exciting. By allowing a model to smoothly learn its own difficulty thresholds, we break completely away from the rigid inefficiencies of standard architectures. So I'm going to leave you with this final thought. If today's AI can natively learn to skim text just like a human, smoothly ignoring the predictable to focus its energy on the complex, just how staggeringly fast and efficient will tomorrow's massive models become? Thanks so much for joining me on this explainer, and I really hope this sparks some amazing ideas for your own work.